So it's a great pleasure to have Prateek as a today's speaker for online turbulence seminar. So Prateek did his engineering physics from IIT Bombay. Then he went to Princeton to do his PhD. And then after that, he went to Berkeley. And he's a leading expert in computational astrophysics. So he will tell some of it today. And after Berkeley, he came to IISc Bangalore in 2011. He's very well known, and for some of his work, he got this prestigious Swarnjayantri Fellowship, which is continuing right now. Okay, so Prateek has wide interest in simulations, galaxies, various mechanism of cooling and heating in galaxies. So we'll hear some of it today. Okay, Prateek, all yours.
Okay, thank you, Mahendra. Thank you for that nice introduction. So I'll be talking about turbulence in galaxy clusters, and this is actually work done mainly by Rajshekhar Mahapatra, who is a PhD student at Australian National University, and with Christoph Federath, who is a PhD thesis supervisor of Rajshekhar. And the work that I'm going to describe has appeared in these three papers. So let's get started. So first, I'll give you a bit of the background, since the audience is familiar with turbulence, but not necessarily with astrophysics. So these are the objects that I'm going to talk about. These are galaxy clusters. These are the most massive gravitationally relaxed objects in the universe. Right. So here is an optical image of a galaxy cluster, Abel 1835. Now, there are like thousands of such objects which people have studied, like hundreds to thousands of galaxies, and these objects extend to size greater than a megaparsec. Just to give you the scale involved here, this is about 100 times bigger than the size of a Milky Way disk, stars in the Milky Way. And in fact, here these orange sort of smudges are galaxies. This is not a very high resolution image, but these are elliptical galaxies within this galaxy cluster. So in optical, what you see are a lot of galaxies, mostly elliptical, red elliptical galaxies. This is the X-ray view. In X-rays, around keV, you see the intra-cluster medium, this hot diffuse plasma, which fills this space between galaxies of this galaxy cluster. Okay, and so this is X-ray, this is optical. On the right, what I show is something called the thermal SZ. So I'm showing this signal. So this is not a direct observation, it's not an image in millimeter, but it is processed to get this thermal SZ signal. So SZ stands for Sunyaev-Zeldovich. So basically, this effect is the upscattering of the cosmic microwave background photons by the hot electrons in this intracluster medium. These hot keV to 10 keV electrons are the ones which are emitting bremsstrahlung and line emission from this X-ray emitting hot plasma. The same hot electrons can upscatter the CMB photons by Compton scattering. And this gives a signal which is used to detect galaxy clusters. And this signal is actually proportional to the pressure times the path length along the cluster. Okay, so there are multiple probes in different wavebands to study galaxy clusters. And from these probes, we know that most of the gravitational support in galaxy clusters is because of dark matter. In fact, 80% of the total mass of galaxy clusters is in dark matter halo, which is spherical, mostly spherically symmetric. And most of the baryons, like normal matter, is not in these stars in these galaxies, but in this diffuse hot plasma called the intracluster medium. So about 80% of the total matter in the galaxy clusters is in dark matter, roughly 18% in X-ray emitting plasma, and only few percent in these stars in these galaxies. Clusters are very, very important. They can constrain cosmological parameters like accelerated expansion of the universe and so on. But for cosmological applications, we need to convert observables like these in X-rays, optical, and millimeter to a galaxy cluster mass. Now, I'll talk about this intra-cluster medium, this diffuse hot X-ray emitting plasma that I mentioned in the last slide. These are two nearest clusters. On the left is the coma cluster, as observed by XMM Newton. So this guy is very big on sky. So you have to look, do multiple exposures so you can put them all together and make this mosaic of these observations. So you can see these are almost spherically symmetric or circularly symmetric surface brightness maps of X-rays. And it sort of shows that the clusters are almost spherical objects. And what you see here are basically X-ray photons in this energy range obtained by XMM Newton. And these labels are just, galaxies within this. So as I showed in the previous slide, galaxies are not easily visible in X-rays. They are visible in optical, but we know their location. So this is coma cluster. This is another galaxy cluster which is nearby, called the Perseus cluster. And this is different, somewhat different from this coma cluster. So these are essentially two classes of galaxy clusters that we study. Coma is an example of something called a non-cool core cluster, and Perseus is a cool core cluster. Cool core clusters are very, very interesting because in their cores, like in this central part. So here, this scale length is 20 kiloparsec, whereas here it's this scale is like 300 kiloparsecs. It's a factor of 10 zoomed in the center of this intense X-ray emission. Here you see in the X-ray maps there are cavities, lack of X-ray emission, and at the location of these cavities you see radio emission. Right, this radio is powered by accretion onto the supermassive black hole at the center of this galaxy cluster. You also see filamentary cold gas in optical and even in soft X-rays. You can actually see filamentary stuff even in this X-ray image. So you see multi-phase gas in the cores of cool core clusters like Perseus. So these are quasi-spherical extended atmospheres. And the X-ray is optically thin, so you can actually see through them and learn a lot about them through X-ray, through X-ray maps and spectra. Intracluster medium, this hot diffuse plasma, is roughly hydrostatic. From modeling the X-ray emission in these spherical shells, we can find out about the density, temperature, pressure profiles of this hot X-ray emitting plasma. So this is like a temperature profile as a function of radius for a bunch of clusters. And you see that the temperature variation is not that great. It's sort of within a factor of 3 for all these galaxy clusters. And these clusters have different temperature ranges. So the hotter clusters have deeper potential wells. They are more massive. And they roughly satisfy this hydrostatic equilibrium. This is the temperature profile. This is the density profile. So this is the gas density profile, this ICM density profile as a function of radius. And once we know the pressure, right, density times temperature gives us pressure, we can apply hydrostatic equilibrium and obtain the gravitational profile, the G, which is enclosed, GM enclosed divided by R square. So we can get gravitational profile and we can get the density profile for the confining matter. And this is this rho total obtained from this. So once you know enclosed mass, you can get the density, the total density, not just the hot X-ray emitting plasma, but the total density which is dominated by dark matter. So this is essentially the dark matter profile. So not only through this, but also through independent measurements like gravitational lensing, we can get an estimate of mass distribution, total gravitational mass distribution in galaxy clusters. And the two match to good precision. There is a slight hydrostatic bias because there is turbulence and infall and non-thermal pressure. So this hydrostatic equilibrium is not perfect, but this is good to within tenths of %. Okay. So, so as I mentioned, there are a lot of observational tools through which we can actually learn about galaxy clusters. So these are actually observational profiles, which is very impressive. These objects are so far away, and yet we know so much and so precise information about them. The other information that we have about the intracluster medium is that it is stably stratified. So these are entropy profiles for a bunch of galaxy clusters. This is an X-ray sample of galaxy clusters, and what is shown is entropy as a function of radius. X-ray astronomers studying galaxy clusters use this temperature divided by density to the 2/3 as proxy for entropy, and this is actually the relationship between. So this is the entropy gradient, and this is the Brunt-Weissela frequency. If we have a stably stratified atmosphere like this, where the entropy increases with radius or density decreases with radius, we can actually define this Brunt-Weissela frequency like this, and we can express it in terms of this K, the X-ray entropy. And if you have a stably stratified atmosphere, such an atmosphere supports internal gravity waves whose dispersion relation is given here. Omega square equals K squared by K squared N squared, or omega square equals N squared sine squared theta. So, the takeaway from this is intracluster medium is stably stratified. Now, if it is stably stratified, we can actually estimate something called the Richardson number or a Flude number, which quantifies stratification of this atmosphere. So Richardson number is defined here. It's the ratio of N squared L squared to VL squared. So N is the Brunt-Weissela oscillation frequency, this one. And since we know the pressure and density profiles, we know N squared very well in galaxy clusters. And then we have L squared by VL squared. So capital L represents the driving length of turbulence, and V sub L is the eddy velocity at the driving length. So this is, basically largest velocity of the largest driven eddy. So this is Richardson number. It's sort of ratio of the buoyancy force to the turbulence, turbulent force, essentially, V dot grad V. Sometimes we can also use something called the Flude number, which is inverse of Richardson number. So it goes like Ri to the minus a half, and Flude number is commonly used for strongly stratified turbulence. And for strongly stratified turbulence, as I'll talk later, it's important to distinguish between the parallel direction, which is the direction parallel to gravity, and the perpendicular direction perpendicular to gravity. So in strongly stratified regime, the eddies become horizontally aligned. So that's why it's important to distinguish between V perp and V parallel. So this is Flude number. So galaxy clusters are actually moderately stratified, as you can see here. So this is a schematic plot of Richardson number as a function of radius for galaxy clusters. Some typical numbers for turbulent velocities I have put, and some typical driving lengths. This is from Rajshekhar's paper. So these are for cool core clusters. Don't take these profiles very seriously, but this is just to give you like a sense of how stably stratified these clusters are. And this red corresponds to non-cool core clusters. The point to take away from this is Richardson number is almost always less than 10. So you are in moderately stratified limit in galaxy clusters. Unlike Earth's oceans and stratosphere, which can be strongly stratified. The other thing that we know very well about galaxy clusters is that the turbulent support is small, and the Mach number, the ratio of turbulent velocity to the sound speed in the medium, is less than a half. So you are sort of in the subsonic regime. The turbulence in galaxy clusters is driven by mergers. You have galaxies falling into these galaxy clusters, and these galaxies are embedded in dark matter halos. So as they move through this intracluster medium, they stir the system. Similarly, as I showed in the case of Perseus, you have bubbles and cavities blown by central supermassive black hole that can provide mechanical heating. And this is actually very, very important to galaxy cluster thermodynamics, but that's something that I am not going to talk about today. Now I'll actually move to some observations of intracluster medium turbulence. So till now I talked about observations of profiles like density, pressure, entropy, and so on. But since we are interested in turbulence because of multiple reasons, now I'll actually show you some observational probes of turbulence. So here is a recent example of direct measurement of turbulence in Perseus galaxy cluster. So this is the same galaxy cluster that I showed previously. This is Perseus. So that direct measurement of turbulence that I'm going to talk about is from this system. And it sort of shows the central region. This, the scale here is 20 kiloparsecs. And this is cooler X-ray emitting gas here. So this observation was actually made possible by this Hitomi X-ray telescope, which unfortunately ended because of a space disaster and could only take data for a month or so. So this is the only cluster that it could look at and get a spectrum for. Now this successor to Hitomi, which is called GRISM here, is going to be launched in 2022. These are telescopes launched by the Japanese in collaboration with NASA. So what this Hitomi did was it was able to obtain a very high resolution spectrum, emission spectrum of this X-ray from this galaxy cluster. And what you see here in red in this graph is the emission spectrum from, and it's very high resolution. You can see the x-axis goes from 6.5 to 6.6 keV. And this line that you see here, it's iron 25 line. So this is helium-like iron with 2 electrons, and it sort of shows this emission line. Now this so these lines here give you a sense of instrumental broadening and thermal broadening, right? So you have this blue line is the sum of instrumental and thermal broadening, but the observed spectrum is broader than that. That means there is additional broadening, and that is because of turbulence. So along some line of so this is actually looking at the central region. So there not only is there thermal broadening, there is velocity, turbulent velocity in this medium. So the two add up in quadrature. So this is thermal broadening and this is turbulent broadening, and the two add in quadrature to give you the observed Doppler broadening, which is given by this red fit in this red line. Okay, so we are using this iron ion. So the atomic mass for iron is 56. So what happens is that even though so because of a heavy mass for the iron ion, the thermal broadening is much smaller than the turbulent broadening, and we can actually dig out the signal from this X-ray spectrum. I have to tell you this, that the other X-ray telescopes which are based on CCD have much poorer spectral resolution. So this kind of work can only be done after 2022 when this telescope comes up. So the result from this observation was that the turbulent velocity was measured to be around 280 kilometers per second. This is 3D turbulent velocity. So you multiply the line of sight velocity by square root of 3, assuming isotropic turbulence, and you can actually the density and temperature of this plasma. So you can actually calculate the Mach number of this turbulence, and it's subsonic, as I mentioned previously. Now, this is only rare. This is very rare to get direct observational handle on turbulence in X-rays, because the instrumentation is not capable to give such a high spectral resolution. In absence of that, people have actually used indirect probes turbulence, like the one shown here. So what is shown on the left is an X-ray brightness map of, again, the Perseus cluster. You can actually see the cavities and so on here. So this is surface brightness in X-rays. So what you do is you subtract a smoothed profile from this surface brightness map, and you get a fluctuation map. So this is a map of fluctuations of surface brightness that shows fluctuations in this. And these black regions are the point sources which are subtracted. You have a lot of X-ray emitting point sources, so you have to subtract it. So this density fluctuation in this ICM, intracluster medium, is supposedly driven by turbulence. So there, so you can actually connect this surface brightness fluctuations to the turbulent velocity. So here actually is some sort of a calibration from cosmological simulations that people have done. So this is the ratio of density fluctuations. So power in density fluctuations divided by velocity fluctuations as a function of k. So this is based on cosmological simulations. So in the simulations, you can actually Fourier decompose your density of the projected. You can actually Fourier decompose your density and velocity, and take the ratio, and somehow this shows that the ratio is something which looks like universal. So you can actually convert the surface brightness fluctuations into density fluctuations and get a sense of velocity fluctuations or turbulence in the ICM. So this is the sort of principle behind converting surface brightness to turbulent velocities. There is another indirect probe of turbulence which is based on the kinematics of cold multi-phase gas. So this is again Perseus. In Perseus, you see these beautiful H alpha emitting filaments. So this is H alpha emitting gas, which is at 10 to the 4 Kelvin. So this is neutral 10 to the 4 Kelvin gas, which is emitting H alpha. So N equals 3 to 2 transition of hydrogen, of neutral hydrogen. And what you see here is the projected velocity, so line of sight velocity of these H alpha filaments in this map. So this is the length scale. So you can actually see that there is like a large dispersion in velocity of this cold gas. So you have to keep in mind that this is cold gas, not the X-ray emitting volume filling gas. But the velocity dispersion here can give you a sense of the velocity in the background X-ray emitting plasma. So the idea is that this cold gas is tracing the velocity in the hot gas. So what people have done is they have actually used this projected velocity data and plotted the first order velocity structure function as a function of separation. So you can actually take pairs of points and calculate this velocity structure function as a function of separation between the pair of points, and this is what you get. And you see some sort of a power law and a flattening. And so these authors have argued that this is signature of some sort of a turbulent cascade in the hot gas, which is traced by this cold gas, H alpha emitting gas. And you have this, power law structure functions, and here you're given Kolmogorov and expectations from simple models. Now, why cold gas? Because the line of sight velocity is very easy to measure. Because in optical, right, this is an optical line. H alpha line appears as 6,500 angstroms. So this is in optical, and the resolution is exquisite in optical. So cold gas is used as tracer of background hot gas. And this gives, like, here in this is the range of Hitomi measurements, like 200 kilometers per second for velocities. And these are different regions measured by Hitomi. But so the point is the velocity sort of saturates in the same ballpark regime. And these are estimates based on surface brightness fluctuation. So what the authors are arguing is that you get much better range in spatial scales using this cold tracers than using X-ray themselves.
Okay, I'll make a brief interruption, Prateek.
Yes, please.
This half, I would prefer it to be 3/5, which is Voljunovokov scaling. Right?
Right. Right. So what you're saying is right, but these are just to guide your eye. These are really, this is just, this is just a power law put there. There is no physical interpretation really.
Yeah, but I think the Voljunovokov may be working here. That's what one could try. If it's not tried already.
You can also see, no one has put Voljunovokov stuff here, and you can actually see the range in R is not that much, like a decade maximum. Anyway,
it's good enough, I think. Well, anyway, we try that. Okay, bye.
Now I come to Rajshekhar's work actually. So he has carried out simulations of Icm turbulence. So these are idealized boxes of driven, mostly driven turbulence. So this is sort of the setup. You have gravity in this direction. You're driving turbulence in this sort of middle part of the box. You don't drive in, close to the boundaries. And, these are reflective boundary conditions here at the end of the box. So, there is like a buffer zone, which is there just to make sure that, we don't get very strong boundary effects. In the horizontal directions, we have periodic boundary conditions. So most of these simulations have been carried out using finite volume hydrodynamic codes, Pluto and Flash, mainly Flash actually. And these are the equations that we solve. These are hydrodynamic equations in presence of external gravity. You are perhaps all familiar with this, but we are, again, we are using finite volume. So it's slightly different from a lot of what a lot of you guys do, which is pseudo-spectral. And we have gone up to resolutions of 2048 cubes. So, these are actually, we have done simulations which are actually going up to very high resolutions. And this is mainly thanks to ANU resources. Okay, so I will actually start, so this sort of part describes those three papers that I mentioned at the beginning. So this is turbulent forcing here, forcing term, external gravity here, which sort of represents the dark matter gravity. This is work done by turbulence, which increases the energy density of your box. And this is external gravity, work done by external gravity. So these equations are fairly straightforward and familiar, I'm assuming. So here is a plot from our unstratified turbulence simulations. So in this case, we don't have gravity. So this is essentially isotropic homogeneous turbulence in a box. And we have chosen Mach numbers. So this is RMS Mach number on the x-axis. So we have focused on Mach numbers from 0.2 to like a few, which covers the range of galaxy clusters that we are interested in. And what is plotted here are different quantities. So this is from a bunch of simulations. So each simulation starts at some Mach number, and because because we are using a total energy conserving code, the gas in the box gets heated. So your velocity is constant, but your temperature increases, especially at high Mach numbers. So you have these trajectories in this plot as the simulation evolves in time. But the point is the correlation between various things like density fluctuations and pressure fluctuations are strong functions of Mach. They are functions only of the Mach number. And this brown line shows Mach square scaling. So delta rho by rho RMS goes like Mach square. So this is the scaling that comes out in the subsonic regime. In the supersonic regime, you see, when you're around Mach 1, you see some sort of the relation between density and velocity fluctuation becomes shallower. And we can, this Mach square scaling actually is expected from this relation between the velocity fluctuation and the pressure fluctuation in the subsonic regime. It's nothing but rho v square equals delta p, right? But this strongly disagrees with this density velocity relation from cosmological simulations, which show that delta rho by rho versus divided by Mach number is almost a constant, and it's 1. Now the question is this universality because of stratification. And to answer this question, Rajshekhar carried out simulations with stratification, with gravity. So, mind you, this is the result without stratification, without external gravity. Now, these are snapshots from our moderately stratified turbulence simulation. So by moderately stratified, I mean Richardson number less than 10. So in less than 1 actually. So the hallmark of moderately stratified turbulence is that the eddies are still sort of isotropic. Right? You can still see these eddies are almost circular. There is no difference between the size of eddies in the vertical and the horizontal direction. So what is shown here are actually, this is the projected surface brightness. So basically projected density, essentially. So rho integrated along the line of sight is this left panel. These are fluctuations of this field. And this is a slice. Rather than projection, this is a slice in the midplane. So what's clearly seen is that as you increase stratification, the density fluctuations increase in amplitude. And this is sort of expected. What else? So you can actually see, just by eye from the background density profile that this is much more stratified than that. The other thing that you should notice is that the eddies are, almost horizontal, right? This is almost horizontal. The velocity field is like this, and then like this. The vertical extent is suppressed. Okay. Now, to be more quantitative, we actually see that the x square, y square, and z square velocities are similar if Richardson number is less than or equal to 1. Again, Richardson number is the ratio of the buoyancy force and the turbulent force. So the buoyancy force is not dominating in this regime, the moderately stratified regime. And what happens is that in a moderately stratified box, part of this energy that's put in the velocity field gets converted into buoyancy potential energy. So you can actually define a potential energy which is related to the buoyant response of this plasma. So the buoyancy potential energy per unit mass is just n squared delta z squared, right? This is like k squared x squared for a harmonic oscillator, half kx squared actually, half kx squared type of a term. Now, so this is n is the Brunt-Weisselot frequency, delta z is the vertical displacement from the mean position, and we can actually relate the displacement to the density fluctuations by this. So this is the expression for buoyancy potential energy. Right. So when we were actually doing this work, we were really benefited greatly by Mahendra's book on stratified turbulence, buoyancy-driven turbulence. So we could actually gain a lot of knowledge in the existing field because of this. Because the literature in astrophysics really does not talk about a lot of this. Okay, so what's plotted here on top is the kinetic energy in the z direction. And these simulations were such that the Mach number was sort of fixed. So all of them have similar z velocity, turbulent z velocity. And what's plotted in the bottom is the potential energy, which is this. Basically energy stored in the buoyant, energy stored in this buoyant displacements is here. So this is with increasing Richardson number, and you see that as we increase the Richardson number, this delta rho by rho increases, as I showed in the previous snapshot, and it also seen here in this time series. These are volume averages as a function of time. So what Rajshekhar did was plotted the amplitude of density fluctuations quantified by this sigma s squared, which is like the RMS width of the density PDF. So this is S. So log rho by rho bar. And what we saw was that the PDF of density is very close to log normal. So this is density fluctuations as a function of Richardson number. So if you recall in our non-stratified simulations, which corresponds to Richardson number of 0, we got some answer, right? And there was a mark squared dependence, or for sigma s, and for sigma s square it was marked to the 4 dependence. So we came up with an expression for density fluctuations in the moderately stratified limit. So here is sort of the scaling, and the data points from bunch of different simulations with different stratifications actually follow the scaling to sort of Richardson number of order unity. Beyond that, our theory is not valid as the eddies become anisotropic. So this is sort of a rough scaling argument. So delta rho by rho square is the sum of density fluctuations due to buoyancy and density fluctuations due to turbulence. And in our non-stratified work, we showed that turbulent density fluctuations square scale with Mach to the 4, right? And this is like a standard result in subsonic turbulence, right? Whereas delta rho by rho, because of buoyancy, is given by this. This is just from the, this is just expressing the buoyancy potential energy in terms of displacement and in terms of density fluctuation. So this delta rho by rho square is given by this, and then we sort of massage this formula and write it in terms of variables that the dimensionless variables that we are interested in. So delta z. So one important thing in deriving the scaling is that delta z squared, the mean displacement in the vertical direction, is proportional to delta z is like a factor of L, the driving length, right? So the point is the eddies are still, maintain the size of the driving scale. So you can actually replace delta z by L, and then, you can actually write your N and G in terms of scale heights and the Mach number and Richardson number. So, it's actually simple to show that, this expression can actually be written like this. So the M is this Mach number, Ri is the Richardson number, HP is the pressure scale height, and HS is the entropy scale height. So, G and N and all these can be written in these scale heights, which is quite convenient. So later on, you will actually encounter this RPS parameter, which is just this ratio of pressure scale height and the entropy scale. And pressure scale height is the height at which pressure becomes 1 by E of its value. So it sort of characterizes the background atmosphere, which is stably stratified. Similarly, HS is the height at which the entropy becomes 1 by E of its value at some radius. These are exponentially stratified atmospheres. Now, this was density scaling, and what you see here is that at low Richardson numbers, you get a constant value. So, and at large Richardson numbers, your sigma s squared is proportional to Ri. So this dotted line shows this formula. So this part of sigma s square is expected from just non-stratified turbulence, and this part is expected from this delta rho by rho buoyancy. So you see, when the Richardson number is small, you get the pure turbulence result, and when the Richardson number is large but still moderately stratified, you get this delta rho by rho buoyancy. So it, simulations actually match this analytic estimate. Of course, there are these coefficients which are determined by the simulations. Now, the interesting thing is delta rho by rho has this scaling with the Richardson number, but the pressure fluctuations characterized by this sigma square log P, the pressure is almost, it's independent of Richardson number, right? There is no variation here. Delta P by P is independent of Richardson number, and it only goes like Mach to the 4th. It only depends on turbulence, does not depend on stratification. And this is actually a very important point. So what it means is that pressure fluctuations are better proxy for the Mach number and hence turbulence than the density fluctuations, which are affected by additional parameters like stratification as quantified by Richardson number and the pressure and entropy scale heights and so on. Now, these are some 2D PDFs that Rajshekhar made. So this is density, and the x-axis is the vertical velocity, right? And this is not non-stratified. This is Richardson number of 0.2, sort of weakly stratified, and Richardson number of 13, little little more stratified. So you see this nature of density velocity fluctuations actually change as your as your stratification becomes stronger. So when you don't have stratification, your density fluctuation amplitude is small. So the breadth in this vertical direction is small, as I showed you in the sigma S plot, right? But as you increase the Richardson number, this broadens because more strongly stratified turbulence gives higher density fluctuations, right? The other thing is that you can actually see this has like a positive curvature. So what it shows is that a fluid element which has a positive vertical velocity is also denser than on average. So what this shows is that a heavier fluid parcel is moved up by turbulence. So this represents this work done by turbulence against stratification, or the conversion of kinetic energy into buoyancy potential energy. Okay, so this is the pressure density 2D PDF, and you see in non-stratified case, pressure and density are sort of related by adiabatic relation. Delta P by P is equal to gamma delta rho by rho, right? But as you increase stratification, the pressure fluctuations, the density fluctuations, which is on the x-axis, become large, and the pressure fluctuations more or less remain the same, as shown in this figure. So these actually give a lot of interesting insights as to what's going on. And you can clearly see the change in nature of correlation with increasing stratification in this 2D PDF. Now I'm moving on to strongly stratified turbulence. So this was moderately stratified, and this is sort of going towards a little bit of strongly stratified turbulence. And you can actually see the nature of this blob, the density, vertical velocity cloud has changed. Now, this is strongly stratified turbulence, and we have actually changed terminology when we did this work. We moved from Richardson number to the perpendicular Fruder number, which is more suitable because the eddies become anisotropic, and we use this. So let me actually remind you what Fruder perp is. Oops. Let me again go back. So this is your Fruder perp. So FR perp, perpendicular Fruder number, is the velocity in the perpendicular plane, in the plane perpendicular to gravity, and this is measured at the driving length. So V perp is the velocity at the driving length measured in the horizontal plane, and L perp is the driving length or the inertial length in the perpendicular plane. In the vertical direction, motions are strongly suppressed, so we don't want to use length scales in the vertical direction, which are affected by strong stratification. So this is Fruder number, just to remind you. Okay, so this is the vertical to horizontal velocity fluctuations, RMS vertical to horizontal velocity fluctuations, as a function of FR perp, this Fruder number. So high Fruder number means isotropic turbulence and weaker stratification. On the left, you have stronger stratification. You can actually see that as you become more and more strongly stratified, the z direction velocity becomes smaller and smaller relative to the horizontal velocity. And you can actually also see that visually by the surface brightness, by the integrated density maps. You see, they are almost horizontal. The contours of constant density are almost horizontal. The fluctuations in the vertical directions are almost invisible, right, when you're strongly stratified. Whereas here, when you're weakly stratified, you can actually see turbulent eddies in the z direction. So this is actually a somewhat complicated plot. So on the x-axis, we have Frude number. So this is actually a collection of like more than 100 simulations that Rajshekhar did, and scanned this parameter regime. So what we have is this RPS, the ratio of the pressure scale height to the entropy scale height, and these are the numbers that he chose. And we have Frude number, so we have like simulations at different Frude numbers, and then we have this Mach number. The color shows Mach number. So the green shades are high Mach number and the red shades are low Mach number. You can actually see that the velocity in isotropy is not a strong function of Mach number, right? The red and green and so on lie on top of each other on this trend, but it is a strong function. The anisotropy is a strong function of the Frude number. Now, for moderate stratification, I showed you the scaling relation, right, which is given here. Delta rho by rho square is, I just gave this. So you had this. So for delta z, you substitute the driving length scale, and you get this scaling. But if you are strongly stratified, in that case, you cannot replace delta z, the vertical length scale, the vertical displacement of your fluid element, which gives you the restoring force, cannot be replaced by the driving scale. It's replaced by Vz by n, the vertical velocity divided by n, and the vertical velocity is actually suppressed at lower and lower Frude number or higher stratifications. So there is a scaling for Vz, which we have put in here. So you get delta rho by rho square because of buoyancy goes like Mach square Frude perp HP by HS. So notice the difference between this scaling and this scaling, right? So this is Richardson number, which is FR perp to the -2. So they actually go in the opposite direction now. The density stratification. So if you become more and more stratified, that is, if your Frude number becomes smaller and smaller, beyond this point, when you become strongly stratified, your delta rho by rho is expected to fall with increasing stratification. And this is physically because as stratification increases, it becomes increasingly difficult to stir the fluid in the vertical direction, and hence to create density fluctuations relative to your background. So this is actually density. These are actually again the sigma s squared, the width of the density PDF as a function of Frude number. So going from strongly stratified to weakly stratified, moderately stratified. You see this, that there is like a peak at moderate stratification and a dip in density fluctuation amplitude at stronger stratification. So this actually happens at around FR perp of around 0.5 or so. Okay, and this corresponds to the same transition Frude number here seen in velocity in isotropy. And this again, like this previous plot, this is a collection of data from a bunch of simulations which span Mach numbers, in the range of expected ICM, this RP by RS, and the Frude number. And you see this data lies beautifully on this analytic scaling that I sort of roughly quickly outlined here. So what you see is here, this is the turbulent scaling, and this is Mach square HP by HS. And this, so when Frude number is large, like of order 1, this is negligible. And you again have 1 by FR perp scaling, 1 by FR perp square scaling, which is nothing but Richardson number. So as you increase stratification, you move on the left, your density fluctuations increase. But beyond a point, they start decreasing. That's when this effect of eddies flattening becomes important, and this suppression takes over. So in that regime, this term goes like FR perp to the -1. So it's sort of this sort of flattens here. Okay, so this is again density fluctuations, this is pressure fluctuations. Again, the same thing. Even with very strong stratification, we don't see much variation in the pressure fluctuations, right? So this is for strong stratification. So, again, the same conclusion that density fluctuations increase with stratification and with Mach number. Like, if your Mach number is high, of course, your density fluctuations are high. But the pressure fluctuations are more or less the same, independent of stratification, independent of HP by HS, as you can see here. So again, this reinforces that whether you're strongly stratified, weakly stratified, unstratified, your pressure fluctuations reflect, more faithfully reflects the underlying turbulence. Now, I am actually at the end of my talk, and this is like my conclusions slide, and a little bit about future direction. So to conclude, galaxy clusters are awesome objects. These objects are so far away, yet from the different observational probes, we can learn so much about them. And what we think is that the density or X-ray surface brightness fluctuations, surface brightness is nothing but density integrated along the line of sight. So these density fluctuations are not a good proxy for turbulent velocity. At least this is what we find in our high resolution idealized simulations. There is dependence on stratification as quantified by Flude number or Richardson number, and this HP by HS, this pressure scale height or entropy scale height. But then the question arises, why do we see such a uniform relation in cosmological simulations? Perhaps the lack of resolution. So the cosmological simulations do not have enough resolution to get a good enough cascade. But this is sort of an open question, at least to me, that why the cosmological simulations show such a universal scaling as opposed to these idealized turbulent boxes. Pressure fluctuations can be probed by this thermal Sunyaev-Zeldovich effect that I mentioned briefly. And this pressure fluctuations appear to be more robust predictor of turbulent velocities, but the angular resolution in millimeter is not that great to get velocity measurements at high K or small scales. The other thing that still needs to be investigated is the role of compressive and solenoidal driving, and how do these scalings change with this. And Rajshekhar is doing this work. And very, very exciting work is happening in multi-phase intracluster medium. I showed you this intracluster medium of Perseus, which shows these cold H-alpha emitting clouds embedded in the hot phase. And people have assumed that they are tracing the hot gas velocity. But one needs to check this in simulations, and the presence of cooling and this multi-phase gas further complicates converting density fluctuations into turbulence. So this was the subject of Rajshekhar's first paper that I mentioned on the first page. So if you're interested in this, you should check that out. CRISM, the successor of Hitomi, will provide direct measurements of turbulence in the intracluster medium. This is coming in 2022. That is next year. So all these things will be thoroughly tested, actually. And last but not least, Mahendra's group has been working on stratified turbulence, doing very high resolution pseudospectral DNS, and focused a lot on power spectra and shell, comparison with simpler shell models and so on. So there's a lot that actually we can learn from you guys, and hopefully you also have some interesting things to take away from galaxy clusters, which are really fascinating objects. So with that, I'll thank you, and we'll be happy to take questions.
So thanks, Prateek. Thanks a lot for a very nice talk.